Every application you build, whether it's a small Go microservice or a huge enterprise system, has a heart. And that heart is its database. It's the library, the single source of truth. So the big question is, how do you make sure that library is rock solid, organized, and fast, instead of, a chaotic mess? Today, we're going to walk through the core principles to build that unbreakable database, looking at it specifically from a Go developer's point of view.
So what's the secret sauce here? What really makes a database reliable? I'll tell you right now, it's not magic. It's a set of brilliant, battle-tested engineering principles that are working behind the scenes to protect your data. And understanding how this stuff works under the hood, well, that's what separates a good application from a truly great, resilient one.
All right, so here's our roadmap. We've got 5 key stops on our journey. We'll start with the absolute foundation, the ACID promise. Then, we'll get into organizing our data with normalization, locking it down with constraints, handling multiple users with isolation, and finally, we'll tackle that constant balancing act between speed and safety with indexes. First up, the ACID promise. Seriously, this is the bedrock. It's an acronym that stands for 4 guarantees: atomicity, consistency, isolation, and durability. You can think of it as the non-negotiable contract that your Go app makes with a database.
So let's kick it off with A for atomicity. This is the all-or-nothing rule. It means that a whole series of operations, say transferring money from one account to another, is treated as one single, indivisible action. If any little part of that process fails, the whole thing gets rolled back. This prevents your data from ending up in some weird, half-finished state.
Here's a perfect way to think about it. Imagine you're booking a travel package online. That single Book Now click has to do 2 things: book a flight and book a hotel. Now, what if the flight gets confirmed, but the hotel booking fails for some reason? Well, thanks to Atomicity, the whole transaction is rolled back. The flight booking gets canceled. You're not left stranded with a plane ticket and no place to stay. It's either the whole package or nothing at all.
Next up is C for consistency. This one's the rule keeper. Its job is to make sure that any transaction only ever moves the database from one valid state to another. You define the rules in your schema, and consistency's job is to make sure those rules are never, ever broken.
Think about a video game. There's a rule, right? A player's health can't go below 0. So if you have 30 health points left and a monster hits you for 50 damage, consistency won't let your health become -20. It enforces the game's rules, probably setting your health to 0, and keeps the whole game world in a valid, believable state.
I is for isolation. Now this is a huge one, especially for us Go developers. Imagine 2 people trying to book the very last seat on an airplane at the exact same millisecond. That would be chaos, right? Isolation is what prevents that chaos. It makes it seem like each transaction is happening in its own little private bubble, one after the other. It's so important that we're actually going to circle back and take a much deeper look at this later on.
And finally, we have D for durability. This one's pretty simple, but absolutely vital. It just means that once the database tells your application that a transaction is complete and committed, that data is safe. It's permanent. Even if the server crashes a millisecond later, the data is still there, usually thanks to something called a write-ahead lock. When your Go code calls tx.commit, you are putting all your faith in this guarantee.
Okay, so we've got our guarantees locked in. Now let's talk about organization. This is where normalization comes in. It's basically the process of tidying up our database schema. We're turning a messy closet into a beautifully organized library. And the reason we do this is to get rid of duplicate data and prevent all sorts of weird bugs when we try to update things.
Just take a look at this table. This is our messy closet. It's a total mess. You can see for Alice, we've got 2 different courses just crammed into a single cell. And Dr. Smith's name is repeated over and over. Now imagine Dr. Smith gets married and changes her name. We'd have to go hunt down every single row and update it. That is a recipe for disaster and data corruption.
So the very first step is what we call first normal form, or 1NF. The rule is super simple. Every cell needs to hold one and only one value. No more lists. So we take Alice's record and we split it into 2 separate rows. It's definitely better, but you can see we still have a lot of that repeating data. Alice's name is there twice, Dr. Smith's name is there 3 times. Not great.
Okay, now we move to second normal form, or 2NF. This is where we start getting smarter. We break the data apart into logical tables. We create one table for students, one for courses, and a third one, an enrollments table, that just links the 2 together. Now, a student's name is only stored in one place, and a course name is only stored in one place. See? Much, much cleaner.
The final common step is third normal form, 3NF. We look at our courses table and we realize, Wait a minute. The instructor's name doesn't really depend on the course, it depends on the instructor. So we split it out again, creating a dedicated instructors table. Now if Dr. Smith changes her name, we only have to update it in one single spot. For most applications, this right here is the sweet spot.
But, and this is a really important but that senior engineers think about, sometimes you break these rules on purpose. It's a technique called denormalization. And why on earth would you do that? Performance. Joining all those perfectly normalized tables can be slow. So if you're building a Go API that needs to read data and respond super fast, you might intentionally reintroduce a little bit of that data duplication to avoid the joins. It's a classic engineering trade-off, data purity versus raw speed.
So we've organized our data logically with normalization, but how do we actually enforce the rules to keep it clean? That's where constraints come in. If normalization is the blueprint, constraints are the guardrails on the highway, making sure no bad data ever gets into your system. There are a few key types you'll use all the time. The primary key is the unique ID for every single row. The unique constraint makes sure a column, like a user's email address, never has duplicates. Not null is simple. It means a field can't be left empty. A foreign key is what links your tables together, making sure you can't create an order for a customer that doesn't exist. And finally, check lets you create custom business rules, like ensuring a product's price is always greater than 0.
All right, let's circle back to isolation, because in the world of concurrent applications, this is where things get really fascinating. As a Go developer, you're probably used to spinning up thousands of Go routines to handle web requests. Well, guess what? You're creating a high concurrency environment for your database by default, and that's exactly what isolation is designed to manage.
This table is really the key to understanding the trade-offs. You've got these different levels, from the loosest, read uncommitted, all the way to the strictest, serializable. As you go down the list, you prevent more and more weird concurrency bugs, but it comes at a cost to performance. Most databases default to read committed, which is a pretty good middle ground. But what's cool is that in Go's database/SQL package, you can often specify exactly which isolation level you need for a given transaction. That's a really powerful tool to have in your back pocket.
And finally, let's talk about the need for speed. Because having perfectly organized, super reliable data is wonderful, but it's not very useful if it takes forever to retrieve. This is where indexes come in. The best analogy is still the old card catalog in a library. It's a separate, special structure designed to do one thing and one thing only: find your data fast. But, and this is maybe the biggest trade-off of all, indexes come with a cost. They make reading data with select queries incredibly fast, but they make writing data, doing your inserts, updates, and deletes, slower. And why is that? Well, because every time you change the data in a table, the database has to do the extra work of updating the index too. So if your Go application is very write-heavy, like maybe it's logging a ton of events, having too many indexes can actually become a serious performance bottleneck.
Okay, so we've covered constraints, which are all about rules and data safety. And we've covered indexes, which are all about performance. They sound like they live in two totally different worlds, right? Safety over here, speed over there. But are they really that separate?
And here it is, the aha moment where it all clicks together. When you add a primary key or a unique constraint to a column, the database automatically, behind the scenes, creates an index for you. Think about it for a second. How else could the database efficiently check if a new email address is already in a table with millions of users? It can't scan the whole table every time. It needs an index to enforce that rule of uniqueness quickly. This is where data safety and performance become the exact same thing.
And that really brings us to the core challenge we all face as developers. These principles give us the blueprint for the perfect, unshakable database. But in the real world, we're always balancing these ideals against the need for performance. So for your next Go project, I'll leave you with this question to think about. Which of these principles are you willing to bend for the sake of speed? And more importantly, why? Answering that is what makes you a great engineer.